I got Mario Kart, Solo.
Okay.
So we're going to start. We're going to pick up where we left off with matrices. Where were we last time? So we're in the linear algebra section, chapter 1. Talk about matrices and matrix algebra. I think the last definition we were talking about was matrix multiplication. So, and I spent some time talking about what this is, but you just need to know how to do it at the end. So let's just recap and talk about how to actually do this. So, let A, B, let's call it, and B, given by P, matrices. Know the dimensions, and we define A times B equals C to be the matrix Cij, and it will be an n by P matrix where Cij is equal to the ith row of A dot product with the jth column of B. And we saw last time it wasn't really multiplication in the usual sense. It's really a model for composition of function, because we looked at matrices as special ways of writing down special functions. And when we plugged one function into another, this was a nice formula that gave us what the coefficients were for the variables. So that's how we define multiplication. Can illustrate with a certain size here. Suppose A is a 2 by 2 and B is a 2 by 3. And again, remember, the inner dimensions, the rows must be the same. Must be the same to multiply. And the outer numbers tells you the size of the result. And another reason we saw that makes sense, because the number of columns told you the dimensions of your input space, where the domain elements are coming from. The number of rows tells you about the output space, or where the range is going. And so, if we start with a function that takes 3-dimensional inputs, outputs them in 2 dimensions, we can then take that and plug it into something that takes 2-dimensional outputs, and it will output 2 dimensions. Ultimately, what we've done is we've created a function that takes 3 dimensions as input and has 2 dimensions as output, and so the outer numbers will give you the size of the result. And so, so the important part to realize is that, notice that it's depending on the rows of A versus the columns of B. So let's say I talked about the rows of A. Let's say I made 2 rows, like A1, A2, A3, A4. I'll call this row vector A1. Let's call this A2 with a vector on it. Let's try the vectors, and we can talk about B. Let's say this was B1, B2, B3, B4, B5, B6. And here I'm going to be focusing on the columns. Call this B1 vector, B2 vector, B3 vector. Then what A, B would look like in this kind of idea is then your AB would look like the following. The part that is in position 1, 1 would be the first row of A dot product with the first column of B. So I'm going to take A1 dot product with B1, and when I do that dot product, the result would go here. The guy that's going to be in the part 1, 2 is going to come from the first row of A dot product with the second column of B. So it's going to be A1 dot product with B2. Put the entire result there. Continue similarly, first row times the third column, you'll get A1 dot product with B3. And there you end because there are no more columns. You've exhausted all columns. One thing I want you to realize is that the first row of the result, it's all using the first row of A. It's always taking the first row of result comes from first row of A. Did someone raise their hand? Yes?
But what do you mean by the jth column? Like, because would that mean B2? Is that the jth column?
I and J are just variables that they count. They count the number of rows or columns. Rows are counted from top to bottom, first row, second row, and columns are counted from left to right, first column, second column, third column. So your I is varying between 1 and 2, your J is varying between 1, 2, and 3, and you want all combinations.
Okay, so which column specifically is the jth column of B?
It changes, it depends on where you are.
In this example? So it's just, that formula is not, I'm not like able to, what is that?
Well, you had, were you here in the last class?
I was. I took all the notes from the last class. I have them all.
Okay, so when you're listing the elements of a matrix, it'd be 1, 1, 1, 2, 1, 1, 3, right? 2, 1, 2, 2, 2, 3, etc. Right? That's the convention.
Yeah, I got that. And
the first number tells you the row position. The second number tells you the column position.
yeah,
I've just defined a matrix that tells me that the ijth position is given by ith column of A, jth column of B. So if this is the 1, 1th position, because it lines up here, that tells me I want the first row of A dot product with the first row of B. In other words, I is 1, J is 1.
Okay, so you just
In
use it
this
as a
one,
variable.
this
I and
tells
J.
me that I'm dot product in the first column of A with the first row of A with the second column of B, and that's in the I2 position, that's this one. Then I'm dot product in the first row of A with the third column of B. So my I is always 1 in the first row, but my J changes from 1, 2, and 3.
That I understood, but since you said I and J, for some reason I was thinking of IJK in a regular determinant. Like that's what it was kind of putting me in the mind of.
No, because that would be I vector, J vector, which is not. I didn't put arrows on top of them. To be specific. So I and J are these are just counting numbers. These are symbols that represent what number of the row I'm currently in. And so I can continue. So I did the first row of A, dot product with all the columns of B in succession. Once I exhaust all the columns, I stop, move down to the next row. So I'm going to take the second row of A, dot product with all the columns of B. That's going to create the second row. So it's going to be A2, B1, A2, B2, A2, B3. I've exhausted all columns, so you'll move down to another row, but there is no other row, so that's the result. you'll notice there are 2 rows and 3 columns. So this is a 2 by 3 matrix, as we would expect. So let's actually put some numbers to this so we can actually see how it works. So example, let A be, let's do this, sorry, the same size. 1, 2, minus 1, 0. Let's B be a 2 by 3. 1, 1, 2, 0, minus 1, 2. Okay. Find AB. The product of these matrices. So now when I ask you to find the product of 2 matrices, you first have to check that we can multiply them, which means you have to check the sizes. What's the dimensions of this? 2 by 2, because it's rows and columns. There are 2 rows, 2 columns. This one is a 2 by 3. The inner numbers must be the same, so yes, you can actually multiply these 2 matrices. The outer numbers is going to tell you the size of the answer that you should get. So if you don't get a 2 by 3 after you do this matrix multiplication, you did something very, very wrong. Okay, so now let's move on. So AB is going to be equal to 1, 2, minus 1, 0, times 1, 1, 2, 0, minus 1, 2, equals. And in the future, I won't write out this much, but I'm going to write out everything right now. So, to get the first row of the result, you need to take the first row of A and dot product with all the columns. So I'm going to take the first row, which is 1, 2, dot product it with this. So that gives me 1, 1, plus 2 times 0. That goes in the first position. First row, dot product with second column, goes in the second position. So that's 1 times 1, plus 2 times minus 1. First row, dot product with the third column, goes in this position. 1, 2, plus 2, 2. And now I end because there are no more columns to go through. Now we've done with the first row, we'll move on to the second row. This row, dot product with that, is minus 1, 1, plus 0 times 0. This row, dot product with that, minus 1 times 1, plus 0 times minus 1. Second row, dot product with the third column, get minus 1, 2, plus 0 times 2.
Professor,
Yes.
would it be okay, like, in the exam, like, since you know that the second one would be 0, so, and you are doing the dot product, so you only care about the first one, so -1, so you don't show 0 times
Always
0.
do it this way.
Always,
Okay. Now, you just simplify. That's just 1.
1.
This is 1 minus 2, minus
-1.
1. This is 2 plus 4, 6. Minus 1 plus 0, minus 1. Minus 1 plus 0, minus 1. Minus 2 plus 0, minus 2. This is your result. Notice that is a 2 by 3. So you did something right. And as long as you did these dot products correctly, that would be the answer.
So you always want us to write it out like that?
No, but especially if you've never seen matrix multiplication before, I would highly recommend you write it out this way. Also, you'll notice that and this is going to be a constant running theme, because you'll be doing a bunch of arithmetic, you'll be doing a lot of arithmetic all at the same time. Each individual step is easy, but when you're doing a lot of these, errors will crop up. So I would recommend also, you'll notice that how I set things out, there's a pattern here. Notice that 1, 0, 1, 0, they're both in parentheses. I can see this kind of symmetry lining up. Same thing here. 1 minus 1, 2, 2, right? I'm always putting the one from B in parentheses and the one from A's on the outside to the left, right? So you come up with these little patterns. You don't have to follow this exact pattern, but I would follow some sort of pattern. Whereas When you're doing all of these and you get to the end, there are times when you're going to realize, oh, I made a mistake somewhere because I know the kind of answer I should be getting is not this answer. And so when you're looking back at what you did, you want to be able to spot any mistakes right away, right? So once you have like a system going of how you set it up, you'll be able to spot anything that's any anomalies easier, okay? So I always set it up very systematically, and ultimately I get the result, and the size matches with what the concept says it should match with. Yeah.
Let's say you have a lot of sets, the matrix, some row and some I and j multiplication would result into 0. Would you mind if we just don't write it? Because it will take, like, considering this for one matrix is it should be easier, but then if there are multiple, and we know that some multiplication will result into 0, like, should we not write it? Because it's gonna take some time to write them out.
I mean, usually it's not going. I'm not going to have you do things that are too big.
Okay.
And secondly, while I don't consider this necessary, one thing it would help with is partial credit. Like if you jump from this to this and that answer is wrong, what can I really say? Do you knew what you were doing and you just made a mistake in one of these things, or did you totally just go crazy? I wouldn't be able to tell, right? So you do this, I'm like, no partial credit, guess you're wrong. Whereas if you do this and I realize, oh, you're only wrong in these 2 positions here, and I can see that otherwise you kind of were doing the right calculations, then sure. So there are reasons why you should write it out and be systematic about things, but
Professor,
technically speaking, I'm not going to require it.
doing the matrices AB, would A be equal to BA, or there would be a different?
Well, let's talk about that. That was the next thing I'm going to talk about. So same matrices. So did you copy this down?
Yes. Yeah.
Okay, once he finishes, I know everyone's I know if that accent, you're like, are you done? Are you done?
Yes,
Okay.
yes.
Let's move on.
That's so true.
Okay, so example. For the above, what is BA? So what do you think?
You can't.
Yeah, it doesn't
You
work.
can't.
It's not.
So if you do B times A, this guy was a 2 by 2. This guy was a 2 by 3. What you can realize here is that these 2 numbers don't match. So here it is, I'm having a function that outputs things in 2 dimensions, and I'm trying to input it in a function that only accepts inputs of 3 dimensions. It's not going to work. These 2 functions do not connect in this order. Undefined. Which brings us to a next important point. Matrix multiplication is not commutative in general. You might be able to find 1 or 2 matrices that they say, whenever it does work out that A times B is the same as B times A, you say the matrices commute. You might be able to find a commuting matrices here and there, but in general, it's not the same. It can be as drastic as this example, where in one direction we can get an answer, the other one doesn't even exist. That's how different they can be. It's also possible for both to exist, but they still give you different answers. So you should never assume. So that means that A times B is not equal to B times A in general. Now this means there are a bunch of things that you'd have to look out for. So we're going to learn to solve matrix equations as well. And so that sort of tells you, if you have an equation with matrices and you multiply both sides by a matrix to simplify things, you have to make sure you multiply on the same side. You multiply by on the left on this side of the equal sign, you must multiply on the left on that side of the equal sign. Order matters, right? And when you're doing distributive law and things, you can't just swap things because you feel like it. It's not going to work. Okay? So for example, if I have A and I'm multiplying out B times C, A is on the left, it has to stay on the left. Right? If you write C times A or B times A, you're wrong. Right? So there are a bunch of things that this will kind of trickle down into all the arithmetic and the algebraic properties, right? You can never just swap matrices on a whim, right? The order matters. It matters greatly. There are times when you can't even find an answer if you don't have the right order. So you have to be very careful when you're dealing with matrices, because matrix multiplication is really functions that are happening, right? In general, f of g of x is not going to be the same as g of f of x. Right? That's just something we know about functions. Matrices are functions, technically. So the composition don't always work in the other order, and sometimes it might not even exist in the other order. Right? So you can think of functions where one is like a radical and one is like a negative number. You'd be able to take the negative of a radical, but you can't take the radical of a negative. Right? The order is going to matter. And with matrices, this is equally true. So you have to be very careful with the order.
For this,
Yes.
wait, A parentheses B plus C,
Yes.
another dividend like AB plus AC, would it be okay to write BA plus CA? Would it be, or the
You're talking about
answer?
here?
Yes.
No, I just said no, it would not be.
So, okay.
A is on the left, it has to stay on the left.
Oh, okay.
So you can write it on the left, on the right too?
Sure, if what you had to compute was this, then your answer has to be this.
Oh,
A
okay.
is on the right, it needs to stay on the right. You can't put it on the left if you feel like it, because you're doing something that might not be defined. So we know how to add and subtract matrices, we know how to multiply matrices.
Can I divide matrices?
You cannot divide matrices. So note. So it's not like I forgot. It's not like I forgot to tell. Oh God, I forgot to tell how to divide matrices. You can't divide matrices. So let's actually just talk about that. Note. There is no such thing as division of matrices. Right? You can't divide yet.
Why isn't multiplying by the inverse the same as division then?
Because the inverse doesn't always exist. Right? The inverse might exist.
Okay.
But again, if you want to make sense of this, try to remember what a matrix was. Right? It's sort of a multi-dimensional function where your inputs have to look like planes. Now, if something looks like a plane and you take 1 over that thing, are you guaranteed to still be a plane? No, right? If I say 2x plus 3y equals 4, right? That's the, well, that wouldn't be something represented by a matrix, that would be this. Can I do this? Is this a plane? It's not, right? So by you dividing by a plane, the result isn't always a plane. So you have to outlaw division, because it won't make sense in how you're setting things up. Matrices, they represent something, right? They represent certain kinds of functions, which if you take 1 over the function, you don't have that kind of function anymore, potentially.
Scalar division?
Huh?
Scalar division?
Well, in terms of scalars, division is like multiplication. Like to divide by k means to multiply by 1 over k, if your k is non-zero. But I'm talking about matrices itself. If you have like, if these are matrices and you have that, you can't like solve for C and say this is B, A divided by B, right? There's no such thing as doing this. Okay. So yes, as Jonathan mentioned, there's something called a matrix inverse, but it's a different kind of animal, and I have to talk about determinants and all sorts of things before I can define that. But there's no such thing as division. Right? So this part of the class it's going to be easier than the calculus part of the class, but the danger here is there are a lot of things that your intuition will lie to you. There are things that you're familiar with real numbers that they're not going to work with matrices. Multiplication is one of them. The fact that division doesn't exist is the other one. Right? There are a bunch of them. Right? You have to remember the matrices, they aren't numbers. You can't really do with them as you do with numbers. Division does not exist. By the way, that being said, I mean, this whole time you've been doing calculus, which we ended the other day, you've ingrained a lot of things in your mathematics that you start to take for granted, right? There are a lot of things that you've been doing that it doesn't work in general. Division is one of them. In the broad scheme of things, if you study mathematics in general, division is actually pretty weird. Like it's very strange when you can divide by something. It's not a typical thing to do. Commutativity is also weird. It's very strange when x times y equals y times x. I know it might not seem strange to you, but because in calculus it's the same. But in most contexts it's not. It's very rare when these things start to happen. So you have to be careful about things like that. What else do we want to define? This one is what you'd expect. But I'll tell you anyway, again for the same reason that I don't want you guys to be taking things for granted. You're like, of course, I want you to understand that we have to actually consider these things. At some point, people had to prove that these things were true. Two matrices are equal. Right, so yes, two matrices, as long as they're the same size and the corresponding entries line up, they are equal. But that's because, you know, if you think of setting two functions equal to each other, and if you look at all the variables and all the coefficients of the variables are the same, then the two functions are the same. Right, so it's not as straightforward as you might think. It's something that you have to justify to yourself. There's also something called a transpose of a matrix. And I'll give you the notation for that. So let A, I'm going to define it this way. Let's say this is an n by n matrix. Then the notation is A with an uppercase T to the top. So when you take a matrix and you raise it to the power uppercase T, that signifies A transpose, or the transpose of A. And that's just this matrix. Notice that the rows and column are switched. Right, so this is called A transpose, or the transpose of A, but I'll usually say A transpose when I'm talking. And basically what it happens here is rows and columns are interchanged. So the first row becomes the first column, the second row becomes the second column, so on and so forth. So, example here, let's say my A is 1, 2, 3, 4, 5, 6. Then A transpose would be first row turns into the first column. 1, 2, 3, 4, 5, 6. Notice that if A is a 2 by 3 matrix, the transpose would be a 3 by 2. Rows and columns, everything gets interchanged, including their dimensions. There are a lot of things we're going to want to do with matrices that are defined in terms of transpositions, and it's also, there's also a geometric interpretation to this, which we might talk about, but we might not. So that's the transpose. Another thing, I said I would come back to this. Why is IN called the identity matrix? What does that mean?
It's like you're multiplying by a scalar. Like if you do.
If it's a transpose, if it gives you this identity also?
No. Yeah?
When you do the multiplication, do the dot products, it'll only take the corresponding component of the matrix. So for the first row and column, it'll be 1 times A 1 1, and then 0 times the rest of that.
Okay, so what is the result of this?
The same matrix you put in.
You get the same matrix back. So that is because, let's say A is an n by n matrix. This means that if I take the identity and multiply it by A, I get A back. It gives you the identity of the guy you multiply it by. It's because it's actually the multiplicative identity. Now that word multiplicative is kind of omitted, but it's implied. So it's basically the identity, because if you multiply some matrix by the identity matrix, it will become itself. What size is the identity matrix here? N. It has to be an n by n matrix. Why? Because the number of rows here must be equal to the number of columns there. We know that In is always a square matrix. And if I have A multiplying by the identity on the right, that is also A, but which identity has to be here?
M.
That's N. Right? Again, order matters. So there might be a different size identity depending on the context. But once your matrices can be multiplied, multiplying by an identity matrix will give you the original matrix back. It gives you the identity of the matrix you multiplied. And that's why it's called the identity matrix. It's a super important matrix. We'll use it again for a bunch of stuff. So that's just something to be aware of. What else do I want to tell you about with matrices?
I have a question.
Yes.
So if, like, let's say you do like 3 times I, which is just changing the ones in the diagonal by 3, right?
Yeah.
That's just, could you just write like 3 times A without writing out the whole thing? You get what I'm asking? Like if you're multiplying 3IN
Yeah.
times A, could you just do 3A on like a test, like to not write out like the whole.
Well, yes, because if I multiply this side by 3, it's the same as multiplying that side by 3.
Right. But what I'm saying is, can you skip like the whole step of writing out I times A?
Yeah, but I don't. There'll never be a context where you kind of have to do
Okay.
that. I mean, it's very rare you're gonna have like an identity in the way. Like if there's an identity in the way of something you want to do, just get rid of it because it's not gonna make a difference.
Alright.
It's the identity. Right, so it's never like, oh no, there's an identity in the way. It's never gonna cause an issue because the. What else? Okay, so I talked about transpose. I'm not sure if we'll get as far as to use this, but there's something called about a symmetric matrix. And we can say A is called symmetric if A equals A transpose. If when you switch rows and columns, it makes no difference, you say you have a symmetric matrix. And this happens if you're, for example, let's say my A is equal to 1, 2, 3, 4, 1. The idea is if you take the main diagonal, everyone across is the mirror image. And so if this is 5, the guy here must be 5. So there's a geometrical component with this as well. But this is just the identity of symmetric. Not going to use that much, but it's something that's nice to know. For my other linear algebra class, I'm arranging a talk for them, and we're going to do all this, so I guess I kind of want to tell you guys enough so that if you're interested, you guys can also watch that talk and actually understand what's going on. Huh?
Extra credits?
No.
When is this talk?
I think it's May 10th.
Online?
Well, no, it's going to be in the class.
Yeah,
But I'll try to record it.
At what time? Can we just show up to your
After
class?
this class.
No, the class is full. There'll be no space for you guys.
Don't
We
stand.
can stand.
Not a lot of you, maybe a few of you. But, so it's like
Mate.
a lot of the matrices, especially in this class, not to even mention the other class. But there are a lot of things where you're just going to be moving numbers here on, and you're going to wonder, like, what's the point of all this? And so I pretty much got someone who actually uses linear algebra in their real life. They actually work for an AI company. And
Wow.
linear algebra is everywhere. You have no idea. Like, computers run on linear algebra, pretty much. And when you talk about machine learning and all sorts of stuff like that, the mathematics behind that is linear algebra. And so I try to get someone who's actually working in the field. They're working on AI models for self-driving cars and stuff, and they use linear algebra in their daily life. So I figured, it would be nice if someone comes and talks about, these matrices things, they're really super useful, and it's not just you moving numbers around. There's a point to all of it. Yeah.
Can you do cofactors? Because in the class before this I had a quiz and cofactors were on it, and I think I did it wrong.
Yeah, well, cofactors we will do, but that's when we do determinants, which I don't think it's going to be today. We're not going to do that. We will eventually, though, so it'll be a while. Maybe 2 classes from now we'll talk about cofactors. Okay. One thing I want to mention to you now is some matrix properties, things that you can apply algebraically and not worry about it because they can be proven that they would work. And then I'm going to talk about one of the applications of matrices, matrix properties. Right, this is the kind of algebra that you can assume will work. Because remember, we're not taking anything for granted here. Things might seem obvious, but they're not. Right, other things that could happen is like, you can have 2 matrices, you can multiply them, and you can get 0 when neither one is the 0 matrix, which is another weird thing. That is also a very rare thing to happen. Just because something times something is 0 doesn't mean that one or the other is 0. That's true for the real numbers, not true in general. It's actually not true for matrices. So there are a lot of things that you might take for granted, so I just want to make sure you know the things that are legal versus the things that are not. And so that comes to us in the form of matrix properties, some things that we can do. And it's really just a list of things that I'm going to write out. So suppose the size is, so if you ever need to simplify a matrix equation, these are the legal moves. Size of the matrices are such that the indicated operations are defined. The following. So A plus the 0 matrix is actually 0 plus A, which is actually equal to A. 0 is called the additive identity. So that's one thing. Two, if I multiply by the 0 matrix on either side, get the 0 matrix. And again, dimensions are of concern here. So if this is an m by n, then this 0 matrix has to have n rows. Right? So you have to be careful with the dimensions. But I don't want to write down all the subscripts, so I'm just going to tell you some ideas you can apply in general. A minus A equals 0. Minus A is just the matrix. This you interpret as that, which is just a scalar multiple of A, which we've defined before. Just take the negative of all the entries in the matrix. Addition is commutative. A plus B is the same as B plus A. So once they can be added, order doesn't matter with addition. It does matter with multiplication. A times B plus C is equal to AB plus AC. B plus C times A is equal to BA plus CA. Order matters. Addition is associative. So if you're adding 3 things together, you can just add 2 at a time, and it actually doesn't matter which 2 you decide to add. So addition is associative. Multiplication is also associative, by the way. So if you're multiplying 3 matrices together, it actually does not matter what pair of matrices you decide to multiply first. You can multiply A and B, get the answer, and then multiply by C. Or you can multiply B and C, get the answer, and then multiply by A. Order matters, though. Right? Whenever multiplication is involved, order matters. With addition, not so much. If you have a constant times A times B, that is the same as the constant times AB. This is the same as A times the constant B. Like constants can pretty much jump around. Right? Matrices themselves, the order matters, but with scalars, just like real numbers, they can actually move around. Here's one thing. And the rule here is very similar to the rule for taking inverses, which we'll talk about later as well. But if I'm multiplying 2 matrices and I'm taking the transpose of the result, the result is the product of the transposes in the reverse order. Kind of call that the shoes and socks law, but I'll tell you why we call it that later on. Might seem crazy to you, but 1 times A equals A. Just so we're clear. Yes, there are times when this is not true. In this class, it's true. Scalars distribute across sums, so that still works, as well as sum of scalars distribute as well.
Wait.
Now, I spoke about the cancellation law for matrices. It's not true. You can't divide by matrices.
Sure, done.
But if a scalar is involved, you can. So if C times A gives you the 0 matrix, then it means either C is 0 or A is a 0 matrix itself. Potentially, it might be a different size. Well, it's the same size, of the same size. So this is like an n by m. This is also an n by m. So those are things that work. Again, these do not work. A times B is not the same as B times A. If you have A times B equals 0, does not mean A equals 0 or B equals 0. You can have two non-zero matrices that when you multiply them you get a zero matrix. As well as if A times B equals A times C does not mean that B equals C. Okay, so you can't like cancel like a matrix from both sides. It's actually illegal to do this. It's not always the same. Of course, there are some stupid examples, like if A is the zero matrix, then both sides will give you 0, but these matrices can actually be different. There are some non-trivial examples though. So for example, I can give you some here, which you can check for yourself. Example, if I set A to be 0, 1, 0, 2, B to be 1, 1, 3, 4, and C to be 2, 5, 3, 4. Then it turns out if I take this times this, and I take A times that, they'll give you the same answer, but clearly B and C are not the same answer. Let me say that one more time. Then A times B is equal to A times C, because they'll, I think I wrote down the answer here. 3, 4, 6, 8. Alright, so if I take A multiplied by B, I get 3, 4, 6, 8. Take A multiplied by C, I get 3, 4, 6, 8. So AB is equal to AC, but clearly I cannot cancel the A's because B and C would not be equal. This is 1.2.
Does not mean B equals 0.
So there are some intuitive things that will not work with matrices, so be careful. But there are other things that will work. One use of matrices will be to solve systems of linear equations in a more efficient way than doing by hand. So that's actually going to be the next section. We're going to discuss that. I believe this is 1.2. Systems of linear equations. We're going to spend a couple sections on this. How to solve linear equations. There are a bunch of situations we can find ourselves in. So I say I give you a bunch of linear equations. They're in a system. And it can be any size, potentially. So let me write out the system in a very suggestive way. So let's say my variables are x1, x2, x3, x4. We can go on indefinitely. So that's one equation. And A's are just some constants. The X's are the variables. And I can have a second set of equations. So this is 1, 2, n. It's n, it's b2. And list going on for a while, but eventually, let's say I end up with m equations. Right, so this is a list of linear equations, right, in a bunch of variables. This is called an m by n system. Why there are m rows, n columns? You'll notice on the left side. Okay. The idea is, what we know about equality of matrices is that if this equals this, I can put one huge matrix, put this inside one huge matrix, and that inside one huge matrix, and the equality will be maintained, right? Because the corresponding components will be equal. Also, by what we know about matrix multiplication, I can rewrite this system. Write that. You'll notice that if we follow our rules for matrix multiplication, take this row times that column, I'll get this line here. The second row times that, I get the second equation. Third row times that, give me the third equation, and so forth, all the way down to the nth equation. This times that, give me this. So notice I just rewrote a standard system of equations as a matrix equation. This here, the system is, there's a standard way to represent this. Whenever we're thinking about the system, we can write an abbreviation AX equals B. And we have names for these guys. A is called the coefficient matrix. Because it's the matrix of coefficients. It's just the matrix that has all the coefficients of all my variables in it, so it's called the coefficient matrix. The matrix X is called the solution matrix. Right? That's just the matrix of your variables. Like if you want to solve the system, your goal would be to find what this vector is. What is the values of all the variables? That would be the solution to this system of equations. So it's called the solution matrix. The B is called the constant matrix. It has a bunch of constants in it, usually. If this also has variables, you'll move them to the other side using matrix subtraction and you rewrite it so that there are only constants on that side. With this, we can represent the system A will be an n by n matrix here. Later on, we're going to see that the size actually does matter. It will determine the kinds of solutions that we can find, and it will determine whether or not solutions even exist in the first place, among other things. But the idea is, given a system of equations, you can throw both sides into a matrix. We can use matrix multiplication to write the left side as this way, and we can describe a system of equations with three matrices. The coefficient matrix, the solution matrix, and the constant matrix.
After, wait, little bit.
Example. Yeah, I have one with nice numbers. Okay, go ahead. I don't know if I solve these later. I should also tell you what this is called. The equation AX equals B is called the matrix equation. For the system. To tackle systems of linear equations using matrices, the first step is to always rewrite them in terms of matrices. So let's say I have a system here. So we can pretend, for example, the goal is to find the intersection of these three planes. This is a system of linear equations. Let's do a slightly larger one. Four variables here. Let's just do those, and then I'll tell you another form that's convenient. So we want to write this as a matrix equation. It'll have that form. Okay. Tell me what this guy would look like. So start with the top row.
2,
3, 7,
3,
7.
1, 0,
1, 0, negative 1,
3,
3,
1,
3, 1, negative 3.
Right. Notice that if a variable is missing, it just means that its coefficient is 0, right? You can imagine there's a plus 0y here. So if anything's missing, just replace it with a 0. We don't lose anything. What would be here?
X, Y, Z.
Right.
X, Y, Z.
X, Y, Z in that order, because I need the 2x plus the 3y plus the 7, so it matters the order that you put the variables in. It should be in the same order that's going horizontally. Do that vertically. It's kind of like you take this row and you transpose it, write it here, and so this would be
5, 2, 1.
5, 2,
5, 2,
1.
1.
B. Again, let's look like this. So first row, what is going to be? 1, 1, 1, 1.
1, 1.
0, 2, 0, negative 1.
0, 2, 0, negative
3, 0,
1. 3,
negative
0, negative 2, 7.
X
x1, x2, x3, x4.
1.
Right, it's like that. Another convenient form. Is the so-called augmented form. Which you can say we augment the system. Or write the system as an augmented matrix. And basically what that does is, when you kind of understand what the variables are, and you realize that, notice that here, these numbers 2, 1, 3, these are all the coefficients of the x. And the 3, 0, 1 is the coefficients of the y. The 7, minus 1, minus 3 is the coefficients of the z. So you kind of saying the variables is kind of superfluous. You don't really have to write it. You can kind of ignore it essentially. And so what will happen is you can write it in just one big matrix. The 2, 3, 7, 1, 0, 1, 3, 1, minus 3. And what you do is you write a line, like a bar, and then you write the other side here. And it's understood that the first column is the x column, the y column, and the z column, but you don't write it. You just write this, and this is called the augmented matrix. B will be similar, so you just have a bar that separates the coefficient matrix from the constant matrix. Augmented matrix for B. So we'll stop there. Next time we'll actually use these forms to do something. By the way, if you ask a computer like MATLAB or something like that to find the intersection of the three planes, what MATLAB does is it first turns it into this, and then it does a bunch of things with it. So we're going to do it next time. So I'll see you guys on Thursday.